This is next on my list, the integral test. Given an infinite series, for which there is some function that agrees with the nth term of my series as in ranges from 1 to infinity. If f is continuous, positive, and at least eventually decreasing, I should have said over the interval from 1 to infinity, then the series in question converges as a series, provided this thing as an improper integral converges as well. Also, the series diverges, again, as a series, provided this as an improper integral diverges as well. Now, don't take this the wrong way. Just because I find out that this integral right here converges doesn't necessarily mean I know what this series converges to. Gosh, did I just end a sentence with a preposition? Sorry. Regardless, I can at least determine whether or not my series converges or diverges as long as these three conditions are met. So let's give it a shot. Now, I admit, when it comes to using these series, this is probably the last series I'd want to use because it's too much work usually involved in showing its premises are being met. So let's check those premises or those prerequisites. Consider a function that's continuous at least over the interval from 1 to infinity, whose output is this, but agrees with the nth term of the series when x is restricted to the natural numbers. Now, number one, if you don't mind, after all, that's a rational function whose domain's all real numbers, so no vertical asymptote, certainly no holes in the graph. Do you mind if I add something in here real quick, like I did not have in my definition? Again, I see no sign changes when x is bigger than 1 or equal to 1, and so clearly the output's always positive. Now, as far as decreasingness is concerned, do you mind if I don't use any calculus? I don't think I need to. Notice how there's only a variable expression downstairs. That being the case, well, maybe I shouldn't use the word clearly too many times. Let's take a peek at these two. I think by definition, the output of f, that would give me this. Again, by the definition of f, the output would be this. Now take a peek at these two fractions. Notice that they have the same numerator, but this denominator is larger than that denominator, so I think this fraction is going to be smaller than that fraction. But that, of course, necessarily implies my function is decreasing, at least for values of x, satisfying this. That being the case, I've met the three requirements to be able to use the integral test. So now let's actually look at the corresponding improper integral. Now, yet again, I'm running out of room. I need all this shown, but let me go and give myself that needed room. I need to see if this improper integral converges or diverges. However, it is improper, so let's you and I rewrite as a limit of a proper integral. Now, this function here is easily antidifferentiable. And anti-differentiating, then evaluating from here to here. But that means the sum proper interval converges. Therefore, the original series converges.